Hi everyone, Senan on this side, and in this video we are going to solve this Geeks for Geeks problem of the day, which is the majority vote problem. So before we get started, I just want you guys to know that the whole PDF solution for this problem is provided in the description below. You can just check out the GitHub link and you can download this whole PDF with my C++ solution. So yep, let's get started. Okay, so there are a couple of things I would like to discuss. One, there is some problem with this particular question, and I'll tell you after I go through this whole actual solution that we are going to actually see, and that is actually present in my PDF. But then I'll discuss one problem that I found. I could be wrong, but I'll discuss that in the end. So you need to find the majority vote. You are given an array of integers nums where each number represents a vote to a candidate. Return the candidates that have votes greater than 1/3 of the total votes. Greater than, not greater than equal to, exactly greater than. If there's not a majority vote, return -1. For example, you see this test case, right? You have how many? You have you have four occurrences of number 5, and you have 5 occurrences of number 6. The total number of occurrences is what? 6 plus 5, 5 plus 4, which is what? 9, 10, 11, 12. So 12 and 12, 12, right? 5, 6, 7, 8, 9, 10, 11. Okay, so 11 numbers are there. So 11 by 3 is what? 9 by 3 is 3. 11 by 3 is 3.6 something. So you see, number of occurrences is 4 for the number 5, so it's more than 3.6. Similarly for this 6's as well, the number of occurrences of these 6 are more than 3.66. In this case we have 5 different elements, so no element occurs more than n by 3 times. Yep, expected time and space complexity, and this is actually a classic problem which is known as the Boyer-Moore's algorithm, or which I like to call as just the Moore's algorithm for counting the vote. A couple of things is that you cannot have more than 2 candidates in the answer. You could have 0 candidate, you can have a single candidate, and you can have 2 candidates. You cannot have more than 2 candidates as a part of your answer. Now, why do I say that? The only reason for that is return the candidates that have votes greater than 1/3, right? So if any candidate has more than 1/3 of share of votes, 2, we can have more than 2/3 share of votes allocated to exactly 2 candidates. But when I say you have 3 or more candidates, that you mean for that, basically it means that you have more candidates than you actually have. So you cannot basically have more than 3 candidates because every candidate has more than 1/3 votes. The total number of votes, the probability or the portion of total number of votes is actually greater than 1, which cannot be the case. So that is why you only have 2 candidates. To solve this, let's look at the Moore's algorithm, because that is a classic algorithm. I won't be discussing each and everything. I would be discussing the intuition, the idea, and why this is a good option. So let's discuss. So since we know we can only have 2 candidates, so I initialize 2 candidates, candidate 1 and candidate 2, and I declare 2 counts. For candidate 1 I have count 1, for candidate 2 I have count 2, and min votes that you actually require is nums.size by 3, right? You can greater than 1/3. So I get this 1/3 value and I check the greater part in this if statement. We'll discuss this a bit later on. Now the classic way is, now let's look at each of this if and else statement. The idea is you go through all the candidates which is present in this nums list. What do you say? If that number is for same as candidate 1, that means candidate 1 has a vote. So increment the counter for candidate 1. Similarly, if the num is equal to candidate 2, that means there's a vote for candidate 2. Increment that counter as well. Now after that, what you do is you check for, let's say, if count 1 is actually 0, right? There are no votes for this particular candidate. What do? You assign that candidate to this new number and you start the counter by 1. Similarly, you do this for count 2. If count 2 is 0, that means candidate 2 has 0 votes. So that means since he has no votes, he cannot technically be our possible candidate. So you reassign them by this. You reassign candidate 2 by this number and you set the count as 1. Now, let's say you found a number that's not the candidate 1 or candidate 2. What you do is you decrement the counter 1 as well as counter 2. This was the goal. Now, what is the intuition behind this? Let's say you have a list of few numbers. Say 1, 2, 3, 3, 2, 1, 2, 3, 3, 3, 3. And I assume that the number of 3's is more than any other number in the list. Let's add a 2 as well. Now initially you see I have initialized int min for both candidate 1 and candidate 2, and my count is 0. So in the very first iteration, when you go into this for loop, you won't go into these two if or else statement. Why? Because as you know, the nums of I is minus 10 to the power 9 to positive 10 to the power 9, and you have initialized this to a number which is outside this range. So this is somewhere it's even, this number is even smaller than minus 2 into 10 to the power 9. So that is why it is not inside this range. So in the very first iteration, these are the only two possible things that would happen. So what happens is, when I go into this iteration for the very first time, assuming this is my test case, so I see this one is neither candidate 1 nor candidate 2, and count 1 is 0. So what I do is I say candidate 1 is this number. So I know my candidate 1 is equal to what? It has an occurrence of 1 vote. Similarly, for candidate 2, it's currently not initialized within the range. So since we've done with this, I'll go into the second iteration. So I'll check for this 2. So candidate 1 is not 2, it's 1. Candidate 2 is int min, again not 2. Count 1 is not 0 because count 1 is for candidate 1, which is 1 right now. So we go into this else if say. So count 2 is actually 0 in this case. So candidate 2 is, I'll say candidate 2 is what? Is actually 2 with occurrence. This is 1 with frequency 1. So let me just clear this out. So what I have is the candidate and its frequency. Now I've seen this 2. Now I'll go to this 2. I go into this loop. I find that candidate 2 is actually equal to this. So I have a vote for candidate 2. I'll initialize this with, I'll do this, I'll increase the value. Now the only problem that you would actually have is that you don't actually know that candidate 1 is actually 1 and candidate 2 is actually 2. It is like saying that you already know that this is your candidate which has more than n by 3 votes, right? But let's go on with this. Now I see this 3, right? When I see this 3, I know it's not candidate 1 nor candidate 2. I also know that the count of both the candidates is more than 0. So we don't also go into this else if statements. So what we are left with is this. So what we do, you decrease the value of the frequency of both of them. Okay, now candidate 1, the count for candidate 1 is 0. Now in the next iteration, what I do is I go to check this 3. I see it's not candidate 1 nor it is candidate 2, but I know that count of 1 is actually 0. Frequency is 0, right? Count of 1 is 0. So what I do, I say now my candidate 1 is not 1, but it's now 3 and the frequency is 1. Okay, so I'm at this position. Now I see this 2. I know it's this candidate, so I'll increase the frequency back to 2. I see this 1 is neither my candidate 1 nor it is my candidate 2, so I'll decrease the frequency of them. So this would be 1. Now I see 2. I know I can increase the frequency of this candidate 2, and then I see 4 consecutive 3's. So I'll increase this counter to 4, right? So you have candidate 1 and candidate 2 as a possible solution, right? And why is this the case? Why do you know that only these two numbers are a possible solution? So the idea, the logic, the intuition behind this is the most difficult part of this video, this question, and this algorithm as well, is to understand that if there is a number which has occurrence more than 1/3, it has the power to cancel any other number that has less than n by 3 occurrence. So you see, number of occurrences of 1 is exactly 2 in this list, and we have 2's and 3's, so we were actually able to cancel out. So the cancellation process is right here. Okay, now after we are done with this algorithm, right, you're basically assuming a particular candidate to be an answer, you try to add as many votes as you can. If neither of them are of either candidates, you just decrease the votes for every candidate by one. It's not that the value of this candidate is the number of votes for candidate 3 is 4. It's not that case. Similarly, it's not the case that candidate 2 has the number of votes as 2. It's just cancelling out the numbers which are not candidate 1 or candidate 2. But for some reason, if candidate 1 or 2 itself get cancelled, that is the meaning that they cannot possibly be our solution till that index, right? And let's say we did it till this point and either of the candidates is either 0 or positive, that means it could be or it could not be a possible solution. So but what we're trying to do is figure out till the index I what could be a possible solution, assuming we have not seen the remaining list or the array. At every index, what could be our possible solution? So at every iteration, we are trying to build up a solution till that position. Now, since I said this candidate 1 or 2 could be our possible solution, what I could do is actually I can count the number of elements of candidate 1 and for the candidate 2, and if it is greater than the minimum number of votes required, you take that as a part of your answer. And since we discussed that you cannot have more than 2 candidates, you only have to do this 2 times. Your vector is of size 2. It's of constant size, right? So answer dot size is equal to 0. That means neither of them could be a possible solution. So you return -1 because we cannot actually do this. Because when you go through this iteration, you would have some of the other candidate values stored in these two. Maybe their values could be something else, but there would be a value in candidate 1 and 2, but neither of them could be the answer. Finally, you return the answer if the size is greater than 0, obviously. Okay, so we discussed this test cases. I discussed the idea. Now what is the time complexity and the space complexity? You see the space, this is constant space, and technically since you have a vector of answer, it could have a linear space, but since I discussed that we can have exactly or at max 2 candidates, this is as good as constant space. So the solution is of space complexity big O of 1 as given in the question, and the time complexity is what? This is linear time, just a simple if-else statements. Counting this is linear time. The second if is also a linear time solution. So linear time, and the for loop is again a linear time solution. What you have is a linear time solution with a constant space complexity, and that is the whole idea. Now, I would like to discuss the problem that I had initially with this, because whenever you start, you just try to do it in a brute force manner, right? So what I did was I did not think a lot. I just counted the minimum number of votes. I took an unordered map. I took a vector int answer. And what I did was for all the votes, I increases. So I calculated all the votes for every candidate. And for every candidate, I saw that if candidate's second value, the number of votes is greater than min votes, that is a part of my solution. And in the end, I just do the same thing for returning. And this is actually, if you see, the order doesn't matter of who wins or who loses a election, right? Who loses an election. It doesn't matter the order of the votes. So returning the answer in any order is fine. The problem I had with this is when I tried to do this, it was showing an error because this exact problem is expecting this algorithm itself. If you change the order of this if statement, which should not affect the solution, but you would end up with an incorrect solution in the way that they are trying to evaluate. So that was the idea, because this, what I feel is this is also working correctly. I've checked it for a couple of test cases. It could be wrong. I'm not saying that I did not check this on all test cases, but I feel this is correct because I'm counting every votes, and every vote I'm checking if it is more than min votes, then that is our answer, right? So this problem, for this particular problem, I found that this should accept this. Typically this should accept this. Maybe it won't give the best time or the best space complexity because we are using some space, right? It won't be the best, but this solves it in almost linear time, close to linear time, because we are using unordered map. Worst case could be n square, but the problem is this can return the answer in any order. It depends on the implementation of this map and the hashing function that it uses. So I assume if you try to solve this, and you would be running into this same issue, and that is why you would be trying to see this video solution. It's not that you don't understand this problem or this algorithm. The problem would be that the way that you're returning the answer is not exactly what is asked. Now, my only opinion could be for this particular question is, if you want an answer in a particular order, please specify that. If you're not specifying that, accept any solution that I give, which is a valid solution. Because as a student who is actually preparing for data structures, algorithms, papers, it really demotivates a person if you don't know how, if you're just getting incorrect solution based on the order of your answer and it's not also specified. If it would have been specified, there's no problem with the solution either. Maybe you could ask for return the answer in a sorted order. I could just sort this and return that answer, but the question is exactly expecting this Moore's algorithm, so you have to know this algorithm exactly. And if you're checking this algorithm, I assume you could give it somewhere that use the Moore's algorithm or something like that. Give a hint that how do you want the answer to look like. Okay, so but anyways, this is a wonderful question. If you know this Moore's algorithm, if you could write this Moore's algorithm, that's a big thing. It's a big thing. So yeah, that was the whole video. Before you go away, I just want to remind you that I have a full PDF solution for this algorithm in the GitHub link provided in the description below, so that you don't have to watch any more videos on this topic or revisit the same video again and again. I'm trying to save your time. Uh, Definitely, you could download it, you could share it with your friends, and yep, that's the video. Thanks for watching, and I'll see you in the next one.